Hi friends, welcome to our channel. Let's look at problem 3817, good indices in a digit string. In this video, our plan will be the following. First, we are going to give two solutions. First, we are going to give a solution with brute force. So this will help us to digest the detail. And secondly, we are going to give a linear solution, linear time complexity solution. So this is going to use some arithmetics. So here the problem statement is rather short. So basically we are given a string consists of digits. So here the digits is from 0 to 9 inclusive. So an index I is called good if there exists a substring S that ends at index I and is equal to the decimal representation of I. So here I would say this constraint ending at index I greatly simplifies the problem, right? So we want to return an integer array of all good indices in increasing order. In other words, from left to right when we do the scan. So if you look at example 2, so this is very special, right? Because this is 0, 1, 2, 3, 4. So all the indices are good indices, itself corresponding to the integer or decimal representation. And this example 3 is none. But if you look at example 1, so for index 0, it's there's a string corresponding to the decimal. And also this index corresponding to 1. So it's 11. So here we have a 11. And here 12, also we have a 12. Therefore, these three indices are the indices we're going to return. So with that said, I guess you need to also look at the constraint. So here S has a length bounded above by 10 to the power 5. So this one actually is a problem size assumption. So because S can be very long, so when you do the coding, you need to think of time complexity. But for this question, first I'm going to use a brute force. In other words, I'm going to compare the substrings with the index decimal representation. So this way, actually, if we want to go deeper, so when we compare substrings, there are some advanced algorithms. But for this question, it can pass even if you use some brute force. And because of the speciality of this problem, we are able to solve it using a linear time complexity solution very elegantly. So here, let me first use the brute force one. So I'm going to initialize a result variable. So this one is going to hold the indices. Also for convenience, let's introduce this m. So or you can just without initializing this in based on your choice. Let's do a for loop for I in range m. So here we should get the string representation of this I. So let's do something like this. Length string I. So this will be the length of this string representation, right? So then if we want to compare, so we compare the string, it should end at index I. So we write I plus 1 here. So the length will be I plus 1. So the beginning will be this one, right? Because this index minus this index should be the length. So if this is the case, so equals the string representation of this I, or decimal representation. So this will be a good index. So we're going to do this. So we just need to return the result. The code is short, but here this is expensive. Expensive, right? But there are some advanced algorithms which we are not going to cover for this problem. So you can do a run. Yeah, it passes the test cases, and then you submit. Yeah, it passes the case, but not very fast. So actually, this part is the problem we want to dive a little bit deeper, right? So basically the length. So if your index is between 0 and less than 10, right? So the index, the decimal representation, just the length 1. But if you are greater than or equal to 10 and less than 100, the representation will be decimal representation with length 2. So in this case, you just need to consider two length 2 subarray ending at the corresponding indices. So this is exactly what we can do some work. So in order to demonstrate this procedure, let me copy this solution signature here. I'm going to mark this one as V1. So here, what I'm going to do, first, I'm going to have an n digits. So originally the n digits, so digits should be 1. So here I use this name, but you can understand it as a multiplier. So this is the original 1, corresponding to 1 digits, right? So then n digits next, right? So this will be actually 10 corresponding to 2 decimals. So originally, because you start from 0 and then up to 1, 2, 3, and before you arrive at the index 10, so all number of digits is 1, right? So here, let's use maybe something like this, 10 to the power 1, right? So you can understand this one is 10 to the power, the number of digits. So once you have this, and then we can also first initialize a result variable to hold the indices. And then the current number should be 0. Then let's look at the iteration step. So for I in range, so I just use length n, right? Length s didn't. So you can do the same thing, replace this n here with length s. So what we want to do is this. First, you need to check which substring you are going to look at. So for now, at the very beginning, we just need to consider length 1 substrings, right? But later, if your index is greater, arrives at 10, you are going to look at length 2. So this, so here, if I equals n digits next. So for example, you arrive at 10, right? So then you need to consider length 2 substring. But before that, you just consider length 1. So here I'm going to do n digits, so multiply by 10. So the n digits next is also going to multiply 10. So you can understand that. So between 10 and less than this one, let's say 100, you are going to look at length 2 substrings, right? So this is the row of this if condition. So now let's look at the current number. So how do we do this? So we want to, because you can start from the beginning, we are going to look at, for example, you can think of the index is 2 or 3, but length 1, right? So what we do is this, the current number, so modulo this n digits, right? So because of this modulo operation, because this are the powers of 10, right? So for example, your n digits is currently is 1. So after you do the modulo, you get a 0. Then if you do multiplication by 10, and then you look at the current number. So because this is a 0, you just look at length 1 substrings. But if your I is 12, say, because it's already past this one, so your n digits will be 10, right? So next digit will be 100. So in this case, if you do modulo with respect to 10, you have to get a single digit. Then times 10, you get 2 digits. Then plus a integer between 0 and 9, you get 2 digits, right? So this is the right formulation. So once we have this, what do? We do comparison of this one and the index, right? So this is the right length. This number is the right length with the decimal representation. Then if they are the same, so it must be a valid or good index. So we are going to do result, append this on. So then we are going to return result. So this will be our solution, second solution. Let's run it. So current is not defined. Yeah, so I guess I should write current num. So let's yeah, it passes the 3 test cases. So now let's look at the generic case. Yeah, it passes all the cases actually fast enough. So if you want to do a term complexity analysis, so for this second one, it's rather straightforward. Basically, it's a for loop, and each you have a constant unit operations. Therefore, the term complexity will be linear. Well, for this one, you see this is also a for loop, but because this is not constant, right? It's related to the length of this one. So if you do a, so let's see, term for this one is O of n, and where n is the length of this S. But here it's not, right? So here, if you look at then this one, so for the first one, if you do comparison, you consider one digits, right? So for two, between index 0 and none, you consider one index, right? So this is a O of 10 times 1, and then between 10 and 99, right? This is roughly 100, right? So then because this length is you are going to multiply 2, right? Then between 100 and 1000, so you are going to, this is 901, see? Then you are going to consider 3. Each you do 3 comparisons, right? So then you get the full term complexity. Or for example, if you do 1000, so this is less, right? So this is 999. So this is 100 is 899, right? And then this, from this one to this one, you are going to get 8999, then times 4, right? So you can roughly see this will be say 10 times 1 plus say 10 to the power 1 times 1, then 10 to the power 2 times 2, and roughly 10 to the power 3 times 3. But then if you see, so at most we have 10 to the power 5, so you get 10 to the power 5, then times 5. So this is an upper bound, right? So then I think you can easily add those together, right? So here, this, so you can actually do something. The term complexity will be something like this. Let's call this m is log, the base is 10, right? The base is 10, the n, right? How many, the length of this s. So let's call it m, right? So then you are going to arrive at this. You are going to compute the sum of 10 to the power I times I. Sum this for I greater than or equal to 1, less than or equal to, say, m, right, m plus 1, right? Then that's the term complexity, right? So this is roughly a very detailed analysis. But here, if you use some advanced algorithm for string matching, it will reduce the term complexity. But overall here, I would recommend the second solution for a good solution. Well, the first one is for just a very fundamental understanding. With that said, I guess that's it for the current problem. Thank you for watching.